To start out Chapter 3, we're going to be talking about patterns and inductive reasoning. This chapter deals with a lot of logic problems, so we're going to be taking a break from more of the algebra side of things for a little bit in this unit. So to start here, the definition for inductive reasoning is reasoning based on patterns that you observe. So in example number 1, I'm looking at these numbers here and I want to look for a pattern. And using that pattern, I want to predict the next two terms of the sequence. I'm going from 3 to 9 to 27 to 81. Going from 3 to 9, I can multiply by 3. Going from 9 to 27, I multiply by 3 again. And to get from 27 to 81, I'm again multiplying by 3. So looking at that pattern, I can assume that the pattern here in that sequence is to multiply the previous number by 3. So the next two terms would be 81 times 3, which is 243. And then the next number would be 243 times 3, which is 729. Next example, now we have a pattern of shapes. I see circles with shapes drawn inside of them. I see in that first circle, I have an inscribed triangle. Inscribed just means the shape is drawn inside the circle. Next, I have an inscribed square, quadrilateral, four-sided shape. And then next, I have an inscribed pentagon. So I'm looking at that, I'm going from a triangle to a quadrilateral to a pentagon. Triangle's got 3 sides. Square quadrilateral's got 4 sides. And a pentagon has 5 sides. So I can assume here that the pattern is that with each circle that I draw, I'm going to increase the number of sides by 1 each time. So next, I'm going to draw a hexagon, which has 6 sides. And then finally, my next pattern would be a septagon, which is 7 sides. So let's say that you want to find like the 100th term of a sequence. I could keep drawing circles like for the next 99 terms, but rather than doing that, which would take a lot of time, I can look at the pattern, make a prediction or a rule, and go from there. And that's called a conjecture. So a conjecture is a conclusion that you reach using inductive reasoning. So in example number 2, what conjecture can you make about the sum of the first 30 even numbers? So if I make a list of this, so to start out, my first even number is 2. The sum of 2 is just 2. Next, I would do 2 plus 4. 2 plus 4 is 6. The first 3 even numbers are 2 plus 4 plus 6, which would be 12. And from here, I'm going to start to look at a pattern. I can see here that 1 times 2 is 2, 2 times 3 is 6, 3 times 4 is 12. So it looks like I'm taking the number of terms and multiplying it by the next number. So let's predict that with 4. So using that, I'm thinking that the sum should be 4 times 5, which would be 20. The first 4 even numbers are 2, 4, 6, and 8. And if I add those all together, that's my pattern, and that works out. So now to predict the sum of the first 30 even numbers, instead of doing this pattern 30 times, I see the pattern could be just 30 times 31, which is 930. Sadly, not all conjectures are true. And a counterexample is an example that disproves a conjecture. So some examples here. Let's say that I make a prediction or I make an observation that if the name of the month starts with a J, it's a summer month. Because I see that we have June and we have July. My counterexample here would be January. That counterexample makes that statement not true. It disproves it. And then example number B, you can connect any 3 points to form a triangle. Now I might think about that and think, yeah, that's true, but what if I drew all 3 points to make a line? That's not a triangle, that's just a line. So that picture would be my counterexample.